Let's say that we want to explore, we're doing physics experiments in a lab and we want to explore different kinds of collisions. And so let's say that we get an air hockey table and we just get these pucks, which are of different mass, and we start colliding them and measuring their velocities, etc. So let's just say that we've got two pucks, one M1 and one M2, and they're on a frictionless surface. And let's say M2 is 3 times M1, and we send M1 towards M2 at a glancing angle at speed v. Let's say that we observe that M1 after the collision goes off at 90 degrees at speed v over 2. There, I redrew the picture. Let's say that that's what we observe. And then after the collision, M2 goes off at some angle relative to that initial path of M1, some angle theta. What is the angle theta? So how are we going to find that? Well, it's a collision, and it's on a frictionless surface, so it must be momentum conservation. Momentum conservation. Is energy conserved? It is a bouncing collision, but I did not say it was an elastic collision, so we don't know if energy is conserved. So we cannot assume energy conservation unless you're told it's an elastic collision. All we're told is it's bouncing, so we don't know if energy is conserved, but we do know momentum is conserved. So we can conserve momentum. We know momentum is conserved. The total initial momentum is total final momentum. So m1 v1 plus m2 v2 is equal to m1 v1 after the collision, v1, what we started calling v1 prime, or v1f, you can call it either one, doesn't matter, m2 v2 after the collision, v2 prime. And what's given is, what's given is the initial velocities and a final velocity of m1. But in order to write this, because it's a vector equation, we need to define our axes. So let's define our plus x direction as the original direction of m1, and the plus y direction, the final direction of m1, since it goes off at a 90-degree angle. But anyway, let's just define x and y in that way. And what's then given is, we know that v1, the initial velocity of puck 1, is v in the I direction. v1 prime, the final velocity of puck 1, is v over 2 in the j direction. And v2, we were told it was 0, that it starts at rest. And v2 prime, after the collision, that's unknown. That's what we need to find in order to find the angle theta. So we can go ahead and just plug into the momentum conservation equation. Therefore, and we know that m2 is 3m1. So we can write m1, the velocity, initial velocity in the x direction, plus m2, which is 3m1, so we can make that substitution. So I'm just putting everything in here. 3m1 times v2, which is 0, is equal to m1 v1 prime, which is m1 v over 2 in the j direction, plus m2 v2 prime, which is unknown. So we're solving for v2 prime. And so, m2 was 3m1, and we can make that substitution to reduce our number of variables, 3m1. So I'm making all the substitutions. And, again, you can look at this as either just it's a vector equation with i's and j's, or we could have separated it into x equation and y equation, right? If we separated it into an x equation and y equation, we would have gotten m1 v in the x direction, we would have gotten the initial velocity, the initial momentum in the x direction is mv, and the final momentum in the x direction is, m1 has no x momentum after the collision, but m2 does, so that's going to be m2 v2x. And then in the y direction, we have the initial 0, and the final, we've got m1 v over 2 in the y direction minus m2 v2y. So we could separate it into the x and y direction. We can definitely do that. And if you like that, then we can solve for v2x here, we can solve for v2y here. But that's what, we just have both of those in one equation right here. we have v2 prime, which is an x component and a y component. And what you find is that the x component of v2 prime is given by this divided by 3m1, and the y component is given by this divided by 3m1. Anyway, okay, so either way, what you end up getting is either set of equations, right? You can either use this or you can use this. You can either just use the momentum without breaking it up into x and y. It might be easier to break it up into x and y. We can go ahead and solve for, therefore, v2 prime is equal to, divide both sides by 3m1 of that bottom equation. And so what we get is v over 3 in the x direction, v over 3i, and then in the y direction we get minus v over 6. Minus v over 6 in the y direction. Just go ahead and do out those equations, and that's what you get. So when we're solving for v2x and v2y, or when we're solving for v2, we don't need to know what v is. That's okay. We're just writing it in terms of the things that are given. We don't need to know what m is, and we don't need to know what v is. We're just writing it in terms of the things that are given in the problem. We're given m2 equals 3m1, so we make that substitution, and we're given that v1 is equal to v. So we're making that substitution. So we're writing it in terms of those things, and this is what we end up getting. And so the angle, right, so we don't know what the magnitude of the velocity is, but we can certainly figure out the angle because the v2 has an x component, v2x, which is v over 3. And it's got a y component, which is shorter actually, a y component, which is v2y, which is v over 6. And so the angle, theta, is going to be tan theta equals opposite v2y over adjacent v2x, which is v over 6 over v over 3, which is 1/2. And so therefore, theta equals the inverse tangent of 1/2, which is 26.6 degrees. So this is 26.6 degrees. See, we can figure that out without ever knowing any numbers. Pretty cool. All we have to know is relative things, right? We have to know that the speed slows down by a factor of 2. We have to know that the mass is 3 times. One mass is 3 times the other. All we need to know are those relative things, and we can figure out the angle. You don't need to know numbers. Okay.